Yeah. Yeah, welcome to Coffee Compiler Club. The weather has finally turned, so I'm wearing my shirt. I'm here today to talk about compilers and not necessarily coffee, and anything related to language design and implementation of stuff. Everyone's recorded. We show up on YouTube in a few hours when I get around to it, something like that. Generally, no set agenda. I have a brief war story from the land of hotspot, but then we'll just let the conversation go. So earlier this week, we were talking about lazy initialization on the Discord channel and lazy initialization of classes. And people were saying, yes, it's all good, but you have to deal with things. And one of the things you deal with is non-deterministic init order. A needs B, class A needs class B, needs class C, and which order, A starts running his init needs B. So mid A init, you start B's init, mid B's init, he needs C, mid C init, he needs A. So he goes and picks up an A state that's half initialized, for instance, that kind of random things. So Java has one theory on how it works. Other people have other theories on how it works. One of the things that made the Java init sort of reasonable was they did end up demanding the initialization run on a single thread. So if thread one touches class A, A's init fires off threads two, three, four, who init their own classes for a while, and then one of them wants class A, and he wants to jump in and run things out of class A, which is not finished initializing yet, and it's on thread one. Can thread three run the inits on A, finish the init, grab a half initialized A? What are the options here? Um, and what Java ended up doing was saying if the class is not initialized, only thread one can touch anything out of class A. Now, if thread one recursively by calling class B, calls C, calls back to A, then thread one does that, that's okay, and you get the half initialized, which means you get zero fields for things that haven't been filled. So you have static final constant values, they'll be zeros until they get initialized. And if you call yourself recursively, you do, and you get the zero. Um, but if you're not recursive, then you'll finish and you'll come back out and with the nits for B and C, and you get back and finish initializing for A, but you never allow a cross thread to come in and pick up the half initialized A. If he tries to do so, he blocks. That means that class BCD on threads two, three, four, if they touch class A mid init, that act of touching has to be tested and said, no, it's mid init, you can't have it. Oh, furthermore, you're the wrong thread, you have to block. That turned into having C2 have to put in a thread test in hot generated code because as you know, Doug Lee trying to cause great harm and grief in the universe. Here, the init for class A does a giant parallel computation to come up with some interesting constant, whatever it is. The giant parallel computation spawns a fork join everywhere. All these other threads are furiously trying to run code and they're running hot code. So prior to this particular hack, they would get portions of thread A helper functions hot enough to be JITted and compiled, and the JITted compiled pieces of A, and A hasn't finished his CL init yet. We're looking at the CL init, the static final constants in A that had not been initialized because you hadn't got that far in the A's init. So C2 is busy trying to decide that he's grabbing a static final string whose quote, hello world, whatever the string is, except it hasn't been initted yet. So he gets a zero. And so he's jitting into the code a fucking null pointer zero, whatever, because some other thread has made seal init on A so hot it had to get jitted. So this all turned into a kind of a, flustercluck. Um, and then C2 ended up doing things where if I am mid-compiling code in A, which I have to do because A's init might not be recursive or spawning, it might not be spawning over the threads, but it might be super hot and running all kinds of code. So I'm jitting code for class A that's not yet initialized. Um, The semantics there are he can get a zero, that's okay. And if you do that, bad on you, fine, whatever. Um, but he puts a check in that says if you're the wrong thread, you have to now stall. So C2 will emit a thread check at the head of any compiled method on class A. And then once class A is finally initialized, he'll throw that JIT code away and let you go back to running non-thread checking code. But until class A gets initialized, anything that JITted in A gets a thread check. And if you fail a thread check, you get blocked. Oh God. Okay, now you have to emit a reasonably fast thread check because A calling A is doing a thread check every time, and that can be, has to be cheap enough that in a hot inner loop of some giant blast, matrix multiply transformation, what the hell, it's not killing you in performance. It's just like a giant piggledy mess. So that was that war story that came around from somebody on Discord commenting like, what the heck? Yeah, that's it. That Ryan, that was exactly it. I did a thread check for remote threads and then declared if you are Ryan's writing in chat, good strategy for init guards on global variables. The rule for Java, I don't claim it's a good rule. You say, what's a good strategy? I don't claim it's a good strategy, but it one that a million people live with. If you're on the wrong thread, you get a thread check on the JITted code, and a second JITting happens post init without the thread check.
Yeah,
Um,
so that obviously works in a Java language, but what would you do in a compiled language? Like, so
you have
I've
two
been
versions. There's the
like,
pre-initted, post-initted versions. If you came down the
y-
pre-initted path, you're running down the pre-initted code version, and you have to come out somehow keep them separate. I don't know if you have to clone everything. It makes, I don't know, you could
so
get,
so yeah, I had two kind of implementations that came to mind here. One is I make this function that checks if the variable has already been initialized, and then I inline it. And then it calls the init function if the like has already been initted
to
is
touch the variable, you have
false.
to touch a second Boolean flag somewhere.
Right. So that was like option one was I have
Okay,
this like
wait,
inline thing.
let me drill option one a little more. What's going on with the multi-threaded check? If other
So
threads
it's
are checking the same bit and
so there's gonna be like three states. One is like, okay, not initialized, one is being initialized, and two is um like fully initialized or something
yeah,
like that.
yeah,
So there is a state where so you try and exchange. So like let's say you check it and it's not in the already initialized fully complete state, then you have to go and say, okay, well, I have to call the slow function that actually does the initialization and that does like the atomic compare and
does the
swap and blah
atomic
blah blah blah
swap
blah.
and lock stuff. Okay, yeah, right.
Yeah.
Okay,
And so my first approach was like, okay, I have that and then I make that inlineable,
yeah,
right? And it's a little slower in some ways
yeah.
that it requires that inline access, right? To
You had to
the
check a
variable.
second word for every word in the program. You checked a second word. I guess every global in the program, you checked a second global.
Yeah. So the other option was is you have a patchable function and the patchable or you could make maybe
Yeah,
either a patchable function or you have a function pointer in a table and you load the function pointer and then
yeah.
you
Function
well
from a table
basically
meant that you loaded the function address from a table every time you did a call. That's not super happy
that's
either.
not good. Yeah, so table is probably out, but like the other option is like okay, you have a patchable function. You make the function not inlineable because you can't really do patchable functions if they're inlineable. So you have this non-inline function call, and then what you make you patch the call just to return once it's already been initialized.
Yeah, yeah. So I'm attempting to do something smart and simple, and it's not implemented, but my current strategy is to inline the check, but expose it to the JIT, including enough intelligence about what path you came through so the JIT can say, oh, once I came through this path, all these other classes had to have been initialized already, so I don't need to check for any of them.
So I guess my thought here is like let's say we have a function call that can potentially block, and then we do inline access to the variable itself, right? So there's like a init if not already initted function, and then the variable access itself is inlined, right? Um, But let's say that we have this function, right? Is it better to just do an inline atomic load unconditionally or have this function call that will And initially it will do like the atomic load and then it will do all the like initialization. But after, like we do a JIT patch, basically we patch the code
Yeah.
and then it just returns immediately. Is it better to have like an empty function call or an inline atomic load? Like which
So
would be your
yeah, C2 does a whole lot of let me stop share for a second here. We'll go back to that in a minute. C2 does a whole lot of self-modifying code patching. Um, and there's a whole infrastructure put in place that can be done well over a large code base, a large surface area. Uh, so questions like that where something has to be done once, and then never again, whatever. He'll allow you to inline like that load and branch. He'll just inline the thing and record in the table somewhere. The init can find it. Here's all the different places where this got inlined. When you finally init, you go run to all those places and you whack the code to a no-op. Um, that's not what happens because it's Java. It's a little different, but that theory works for a bunch of things. So all inline caches all start in an empty cached state, and they're inlined all over the map, and so you get, hundreds, thousands of them.
Yeah, my problem here is in LLVM's inlining passes are a little too they transform the code a little too much and they don't preserve like that kind of granularity of patching. So if you
Yeah.
want a patchable function, you can only patch the entry point
So
on
so the
LLVM.
the patching strategy says I put a WAD in that from the compiler's point of view is a patchable call or a patchable test or a patchable X. And then the block of code that goes in is known to be patchable. And it may have internal pieces that can be scheduled, but they're all forced to be scheduled near enough each other that the patching parts, individual patch parts within there will not span a cache line. So you can, in fact, atomically update them using a compare and swap to update the patch pieces. And they're not just function calls or function headers. Function headers definitely have patchable parts, but other things do too. But we had to tell the compiler, here is a special call or special whatever it's going to be, and it has these rules. It's patchable. It
I think
can't.
the
Well,
way you
how
would approach that in LLVM, if you wanted to, would be to use inline assembly, because you could abuse that to set up first of all alignment directives to make the code aligned to whatever you want, and then you could put in weird instructions, and then just either track through the pipeline because LLVM can't remove them from you, so track them through the pipeline to the end, or have the code itself store like cookies that you might be looking for, like, hey, I'm looking for this the thing here and like this sequence. It's like, okay, cool.
Yeah, I don't think I can do that because I think that will block too many optimizations. Like my best thought here is like I with the patching functionality that LLVM provides, I can only patch the entry point to the function and have it jump somewhere else. So, or make it return. Like those are kind of like the options that I see.
That gets into the
So
whole what's the cost of failure to inline?
so I guess the inlining probably is out if of the function, but like is my best option just making and before I enter the function, just having this instant return. Okay, I'm gonna say if blah blah blah. I'm just gonna return if the variable is already initialized, and then that that's kind of
Why are
like
you always
my
calling a function? Why does this involve a call? You're accessing a static, right? Or some sort of global?
yes, but the global might not have been constructed yet, so it's got to
Well, yeah, yeah,
initialize there.
obviously. So you have a bool. You just have a bool and you call the init function. This is like standard call once, basically.
Right. So if I
Um,
use a bool, that's kind of like the if atomic load, let's say acquire ordering is not equal to blah blah blah.
I don't think it needs to be
Um,
atomic in the fast path, right? You could do it like a non-atomic load and just see if it's one or something. And then, if it's
n-
not, then you can fall back to an atomic,
no,
right?
you can't do that, unfortunately, at least not on architectures that don't have total store ordering.
What's
Because
that do?
But what architecture doesn't
Well, you
have
don't need
some
total
form of
ordering.
sequential consistency?
Yeah.
Yeah.
ARM,
What you could do
ARM
is
absolutely has
you could
sequential
probably
consistency if
do
you want it.
like an atomic
yes,
exchange.
but that requires you to set the instruction to be atomic. If it's not atomic, it's not in
No, but this
like
is
You
still
can
not a this is still not an issue. If the value is already set, you go fast path for light and easy. If it's not set, then you go slow, and at the slow point, you throw it on your fences.
Yeah, exactly. This is the point is not to be like safe in the fast path. The point is like assuming your load is, indivisible, right? Like your load can't be teared, which I think should be true for most architectures.
That's
Um,
not true. So if you use the way LLVM works, a non-atomic operation, like there's different memory orderings, but like if I
you
do a
might need to
load
tell
in
LLVM about the fence, but I'm not sure you actually will need a fence in the final
Yeah,
product,
it
the
sounds like
final
more like you'd
binary.
need a relaxed fence where like it doesn't actually
no,
like do any
it needs to
fencing. It's
be a
just like,
quire. It can't be relaxed. It won't
In
work.
the slow path. In the slow path,
wait.
it would be,
Why
right?
can't it be relaxed? Because it sounds like what you need is for the load to not tear, and in which case relaxed will give you that. You don't really need the fence because all you need to be able to say is, hey, has is it zero? And if it's
So okay,
because there's only two options, it could either be on or off.
well, there would be three, but because it
Oh,
could
okay.
be like currently being initialized. So some thread has claimed it and is starting it up, and then so it's more like a tri-state thing. But anyway,
Oh, so you'd break that out into like a two-state thing, so that you have the fast path of it's totally been initialized, and then you have the it has not
right.
yet been initialized,
So
and then
so
not yet been initialized handles has somebody else started, or are you going to do it case.
so
Yeah,
you
like
you
like
have a
like
race.
the important part is that you have the fastest fast path is just I like do some really quick, not even atomic, just see if this byte is one. And if it's already been won through someone else who did all the synchronization, or maybe it was my own thread in a past iteration or
Okay.
something, then I just say, all right, great, this address is known to be
Right.
initialized, and I don't do
So
any work, right? I don't
so
call
you
a
have to
function, I don't have to do anything.
let's say that I have this like guard. If not guard, I'm gonna put this in the doc, right? It's gonna be like slow font initializer. Okay. Guard equals let's say not guard equals done, or hang on, guard.
Don't worry about we got it, not guard, Boolean, whatever. Right.
Well, it's not done. So this is slow
Yep.
initializer, and then use var.
Oop.
Okay. So here's the problem with if you put this access to guard in relaxed ordering, the compiler can go, hmm, temp var like this, and then it
But
does
you don't
this.
have cheap ass
So
volatiles. The
so
land
so
Java comes in with cheap ass volatiles to solve this. Okay.
well, we have this would be like to prevent the compiler from doing this, what you have to do is you have to do guard dot load, and then you use like std memory order acquire like that. That's the cheapest way to do this. And if you compile this on x86, you actually just get a regular load instruction
Yeah.
because
Right.
x86 has implied
I,
acquire on
I'm
load.
not sure if that's possible. The reason why is because like it sounds like we're describing like a load dependent, like or a control dependent load, and
Yeah.
in which case it would be stopped for the same reasons that a normal load can't be hoisted over like let's say a null check.
So that's not true. Well, actually,
Can we
okay.
build a code example of that? Because it sounds like wrong, but I'm not sure if
Well, okay.
maybe
I
there's
guess
something
I
I'm
guess what
missing.
you're saying. I kind of see what you're saying, but the point is, if for one thing, the way LLVM models it, if you access something from one thread and write it to another from another thread, that's kind of like undefined behavior if it's not atomic.
Well, no, no, no.
So
So relaxed is a real atomic like ordering. It just
right.
doesn't impose any
Okay.
ordering.
So say okay. So we say run this slow initializer. Um. So we
We
have the branch.
Does
But okay.
LVM
So
really not have like a memory barrier? Like just like obviously something like like an actual atomic, oh, I'm synchronizing kind of load here is like, you know, that's like a superset of it, right? But really all you need is a reorder barrier, right? You just don't want the CPU or the optimizer to move around your loads in a certain way, right? Like that, like those don't actually need to be atomic. I mean, a load probably should be atomic no matter what, right? At least on like ARM and x86 and modern architectures that
So,
people
so
use. But like,
you're going to get into the situation where, okay, let's say someone writes some data. Okay, let's say they write a struct. Okay, I got my struct here. So it's like struct foo, and it's got int a, int y, right, like this. And then I have my variable foo, my foo. I don't know. This is my global variable. And so if I grab access to this, right, and I don't do, if I load this, I check, okay, foo has been initialized, and I load that in relaxed ordering, that would actually guarantee that the guard for the myfoo object has been set, right? It doesn't guarantee that the data for foo is actually available. Because if a thread writes this data, so like let's say the thread says, okay, this is a guard, myfoo guard. So it's gonna once we have thread one, and it's gonna be like, okay, myfoo guard compare exchange, and it's gonna be not started, in progress, and then blah blah blah. Let's just say if that worked,
Yeah,
and then we're gonna
you're
be in
getting.
here.
Yep.
So say it's just not here. It's just gonna wait, and then return. But let's say that we're in here. It's gonna say my foo equals blah blah, and then it's gonna say my foo guard equals done release order. Okay, so this is thread one. If thread two goes in, and thread two says, okay, if my foo
Oh, but I like my
guard
food. Your
equals
typo was
done.
reliably consistent. It's very funny.
Did I do that again somewhere? Oh
Yeah,
shit.
no worries. No worries.
Uh, auto type. So now I'm in my foo guard equals done. Uh, and
With
then
the
I
done you
say,
got, you can just go use my food.
yeah. So let's say if
Right.
it's not equal to done,
Yep.
slow. Okay, so here it's equal to done, and I say my foo copy equals foo. Now here's the problem. If this is even if this loads in relaxed ordering, this is not set. So like this can be invisible. Like even though this gets released here, it doesn't get acquired here. So this foo variable can just be random junk from this thread's perspective because it's not ordered with regard to this
Yeah.
release here. So
Yeah.
this write into the actual global variable, which is what we actually care about, is not visible to this thread.
The Java volatile exactly solves this.
Yeah.
The
Yeah,
guard
I
is
don't know if
volatile
that's true.
and it gives you
The,
the
Um,
ordering on
this
both
is true.
sides.
This is like the canonical example of synchronized with. So in order to fix that, you have to do load. You have to
Yeah.
set the order to std memory order, and you need at least release to get, or sorry, not release, acquire.
Acquire. Yeah.
Yeah.
Yep. Yep. That's what Java volatiles would do. Yep.
So because this is not an atomic variable, right? So a release will basically say anything that I've done before this has to happen beforehand.
Yeah.
Um, but this has two effects, right? One is the local optimizations. So it blocks these from being locally reordered.
Yep.
But the other thing is it's like a publishing effect.
Yeah. It blocks the other side from being reordered as well. Yeah. You have to, when two threads tangle, they both have to play the dance. Yeah.
And
The other
the
guy has to do his output writes or the output reads. The two loads have to not be reordered on thread two, and the two writes on thread one have to not reorder.
I think the thing that you're missing is that this is like what I would call the slow path. Like anything you're touching, anything where you have to actually touch atomics is like the slow
Yeah.
path, right?
Well, okay, so he goes to
Um,
thread two. So suppose thread two is that's my example I was trying to write there. So he runs a million times in a hot loop. It's hot. You want to do something. So sometime through, he's doing the guarded load and the acquire work, and then he does the foo afterwards because then he loads foo and it's set. And it's all great, except he's paying the guarded low every iteration through the loop.
yeah.
Okay.
So basically all I would suggest is like I think you should be able to just do essentially if my foo guard dot load, I don't know, like no memory ordering, just do a normal load, like
All right.
dereference it,
Yeah, put that in the
and
hot loop
that
so the compiler moves it out of the loop
equals done.
and
Um,
causes you to be screwed up.
well, so I think the important thing, like,
so
so
that does not work.
Yeah,
well,
that's
well,
This
well,
is
so it doesn't
one
work in
of the
isolation, but I
let, let,
think
let,
the important thing is you just need like memory fence, and then maybe like one before for the
Well,
case you
as
have a
soon as
loop.
you did memory fence,
That's
that's your memory order require.
well,
I
memory
mean,
fence
I
Well,
is
no,
think
no,
it's a
no.
little
I
tricky,
think I
right?
know.
Like
I think I see what he's trying to get at. So
this is a reorder barrier. It's not a synchronization primitive. It's basically just
Right.
saying like we
Yeah.
want locally to ensure that this load happens,
Right.
that's
and it's
That's
essentially just the
exactly
fast path that like
that's what like
yeah.
okay, let's
Isn't that identical? You just wrote the same thing.
no, no,
well
yeah,
with the
I
acquire and
think I might
release.
see what he's trying to get to. So imagine we do a relaxed load. So it's not going to get torn, but we don't have very strong guarantees on ordering. There's only
Right.
two values the thing could be. It could either be done or not done, or at least those are the only two cases we care about for this if statement. If it's not done, or if it says it's done, it can't ever go back, right? So
Yes.
if it says it's done, we're good. If it says it's
Yeah.
that
not done, we don't know if it's in the middle of it. Maybe it actually even already finished, and
so
we just got like a
here's the
late answer,
problem, right?
right?
The problem is
Basically, the critical piece is that you only ever do the transition to done when you're, doing all the like proper synchronization. Uh, so if it is
You're
already
you're
done, you
making
know
an
that
assumption
two
which is
threads that
not
agreed.
valid.
yeah. Right.
No,
Yeah.
no,
Yeah.
no.
So
I
Ryan's
haven't finished
So
I haven't
hang,
finished the thing.
let me
There's
well
still a
I know
piece
what I
missing.
know what you guys I know what you guys are talking about, but there's an assumption you are making which is not true. The assumption is that the order that core 1 writes data in is
Yes.
the same order that that data is exposed to core 2, and that is not
Yes.
true on most
No, 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 no.
architectures.
That's not the assumption I'm making actually. So okay,
But
so
that's
now
a valid
here's the thing
assumption from
here.
Ryan. I mean, Brian's got a
Yeah,
point there. That has to be fixed.
yeah, yeah. No, no, no. Yeah, I've got a
Okay,
solution for that. So
go. Yeah, go. Yes.
So here's the deal. So if it says 0, it's possible that the thing could be misordered on the other core. The other core has released it, but we are not necessarily agreeing on the order with him. So like, okay, now we need a fence, but we only need a fence on the slow path. Like we only need a fence if we see that it's not done, because if it is done and we see a 1, then it means it has already been written by the other core.
That is
Uh,
not true
that is not
because it
true.
may yeah, that's not true because you are assuming so think of Einstein's theory of special relativity where
Yeah.
different observers can
Yeah.
disagree at the order of events that happen.
Yeah.
So thread 1 can write to foo and then it can write done, and thread 2 can observe the write up to done occurring before the write to the foo variable. So unless you use a synchronization ordering, the
Yeah.
order of events that they happen in thread 1 and that they're observed in thread 2 are not the same.
I give this talk all the time. It was one of my more popular talks. How many different ways can you get screwed up if you fail to fence on both threads? And the answer is a lot. Brian's absolutely correct here. You have to fence on the reader thread. Now, that fence on an x86 can be really cheap because x86 includes fairly strong ordering, but ARM and other chips do not. You must have the fence on
Yeah.
the reader and the on the writer, both.
Yes, and
Yeah,
acquire is the correct
Yeah.
ordering here. And
Yeah.
actually on x86, all acquire will do is stop the compiler from reordering
Yes.
instructions
Yes.
because it is part of the
It's
hardware
cheap,
memory
right?
model.
It's cheap on an x86, and the compiler has to honor it. And you're done. On other chips, you actually have to have a fence-like thing there. Having the
I
guy
guess
who
I guess the
implemented the
thing I'm not
Java memory
aware of.
model, 100% guarantee those reorderings were common stuff until the memory model got sorted out.
I guess the thing that I'm personally not aware of, I guess, is just in a performance level, like if you emit fences around your accesses versus if you actually do like a ARM synchronized like load store, like LDXR or whatever the equivalent is, um, or whatever you do that has acquire and release semantics. I don't know which is actually faster. Um, my my thinking would be that if you can avoid actually doing the atomic in some way, even if you have to emit some sort of barrier that says like, that tells your hardware like, don't push anything around here. Um, I don't know. You might
That
you might
barrier
get better
is
performance.
as soon as you
Uh, I mean
put
the
that
different
barrier.
instructions, right? There's uh there's the like, acquire and release ARM instructions, but then there's also like what is it, like DSB or something or DMB.
Oh
Um,
God, yeah,
and I
right.
just, I
But
think
there
like
are larger and smaller hammers. But
DMB is like going to be like so let's open like GCC or something on Godbolt, and you'll see that when you compile in like a full sequential consistency order, you're probably going to get that like DMB ordering. But when you do acquire release, you get a little bit lighter weight
yeah, I would believe that.
ordering. So
I
let's
guess
say
here's
like
another thing, which is I wonder if it would also potentially still be faster to do just a load versus starting with a compare exchange. Like if you're avoiding the
Oh no,
like
yeah.
read
If you,
yes,
modify
yes.
right,
yeah, yeah. The,
you
the,
should probably do
the, the
at least
compare
that.
exchange belongs on the slow path, but you need to have a load for the guard, some sort of ordering requirement, load release or load acquire or whatever, and then a load again after it.
So I guess so kind of
Given
my
two
my
bytes.
my question here is, right, so acquire does have some penalty, especially on architectures like ARM where it's not just a load, it's actually a special instruction. My question is like, which is more overhead? Just an empty function call that I've patched out, or uh uh an
Oh,
acquire load?
oh,
That's
I
kind
see
of
what
like
you're
where I was
saying.
getting at.
Yeah, right. So the compiler is prevented from reordering, but you allow the hardware to reorder across the call boundary because you've knopped it out. I, I
Well,
claim I claim the knopping is fine. That's what C2 went with for a lot of these operations.
Well,
They
so
just
I will
pop out.
counter with
They're done.
I had to do something very similar when I was working on WebKit. I was doing some stuff with the allocator, and we had this like nasty configuration check that could not be like I don't know. Basically, we had to add a branch on something that was like synchronously defined. I don't think we had to do. Did we have to do the call once in that path? I actually don't remember. But every single malloc call had to do this branch basically to check to see if something had been initialized. Um, we basically found that like the cost of doing that branch ends up actually being maybe quite a lot cheaper than you expect because, basically just due to prediction. Like
Uh,
even in a case like this where it's pretty complicated, for something like static init, you're very, very likely to basically 100% predict it in the
let me let
over the
me
life cycle of a program.
yeah, let me throw
Um,
out the warning on branch prediction. If you have your branch predictor, if you arrange your branch so that the correctly predicted path doesn't fill the predictor's tables, you're in fact correct. You can have a zillion of them and they'll all predict great and they'll be half a clock cycle. If you throw your branches out willy-nilly, your prediction branches, they're all predictable, but some of them require the branch predictor table to fill up. You'll run out of branch predictor table and you'll be back to random and they'll be expensive. You must get it correct. If it's going to be highly predicted, like after a init, it must not fill the branch table or you'll run it out. But you won't see that effect on small tests and micro benchmarks. As soon as you go big scale, you'll have lots of these branches, your table fills up, and suddenly you're always mispredicting.
Yeah, I think that's a good point. Most of my experience has been in like very specific hot paths. Like there's only so many variants of malloc or something in a whole application. So then, that's a case where that's basically always getting hit. So something like statics in general might be tricky. I think the issue with patching is just like if I think of that from any kind of complexity or security perspective, that seems like such a nightmare to invite on yourself just for static init. Like it is probably faster in the long run. Like if you have a hot loop where all you do is read a static, then yeah, probably patching that out is faster. The process of patching it is going to be a nightmare because it means you have to do like an instruction cache flush and all these like awful
So
things.
these are right, but this
Um,
is a solve it once. If you're going to use this strategy, you solve it once and you use it over and over. So Hotspot
well,
uses that patching all over, and we have a specific patchable path. It certs crap about the code before, it certs crap afterwards, it
if you're
forces
already
that
jitting,
patch.
I think absolutely that's the right move. If you have an LLVM language that is ahead of time compiled and you're considering like patching the binary like
Yeah,
dynamically, and this would be the thing that you add patching for, then I feel like just from like a security perspective, like you probably don't want your application to have the permission to like start modifying its own code. Like that's kind of a nightmare to invite upon yourself. If you're the
well, I
JVM or some other JIT, then like you don't really have that much choice, and so it's like, yeah,
if you're JIT, you
exploit
have
that as
no
much as you
rights.
can, right?
Yeah,
Um, but this is like, I mean, and then also just LVM is not really built for this kind of like patching, is my understanding.
it
So it might also just be
it
a real
it it
nightmare.
has it has a function patch annotation, but the important thing is actually that you don't need to flush the instruction cache because the way that the patch function is designed, there is enough like space in alignment on the function there you can patch the entry point within a single atomic instruction. That's the way it's designed. Um,
Uh, so
you
I'll say
make
from experience, the actual process of like uploading freshly JITted code is not I think that simple. Like, other like another thread may be holding the old version in its instruction cache and just be casually running it in the
Yes, but
background and suddenly get
that's
into an
okay
inconsistent state.
because the
Uh,
shortcut for the patch here is I want this function to just return immediately because it's already like I don't even want to do the atomic load because we're in the
You want to patch the call sites, you don't get into the function. Okay, so C2 hotspot does this shit all the time, including multiple threads everywhere doing all these things. This is like a normal event for it. And some of the patches are monotonic and they can be rerun over and over and over again. It's all okay. And some of them are not and require you to actually flush everyone's iCache. Are not allowed. And those we mostly completely stay away from, but we had to be aware of it and fall through we engineered our way out of the pit hole we hit there. Um, so if you have a patch that's has a monotonic progress like the init guy, and then on the slow path they're going to lock somewhere, and other threads will get caught and hang. Then other threads don't need to flush their iCaches; they'll just trip over the guard uh, lazily when they do, and at that time they'll fix their own iCache by recognizing that they're in the slow path, and then they come back around. They either get out or they have to iCache flushed, so they quit seeing the call and they see the no ops you've patched. But you don't have to do anything eager about it. You can just let them fall over it.
as long as you're
It's
doing the synchronization in the slope path, and I could see how that could work. But I will still retreat to, I think, at least
there's some extra complexity there. Yeah.
well, and also just, I think the number one thing that would freak me out is just here's a LLVM language that has executables that previously would not be modifying its own code, and now it has total permissions on whatever platform
Well,
to
okay, so
modify
there's
its
a
own code.
permissions thing going on here that's different for hotspots. Like the whole process for Java
Oh
hotspot
yeah, yeah.
has the I can write to my own brains. And I do
This
so
this is this is directed at Ryan. I think Hotspot, of course, I mean, I worked in a JS engine which had very similar,
same
situations, and we used patchable stuff
Yep.
everywhere.
Yep.
So, uh,
Now
but
you're saying here I have LLVM, which is typically the binary is frozen. I could say exec permissions only, no read write, no write permission. Oh, but now I'm linking in this library. The library has this lazy init logic because I'm mixing C and Ryan language or C and simple. And the answer is, oh, now the binary as a whole needs to be writable because it's one little piece of it. The DLL needs to be writable because that's the semantics of how that language works. And you're saying that's sketchy, which maybe it is.
it seems
well,
like I would describe it as a large expense, basically, in terms of types of stuff you are now willing to embroil yourself with from like a security perspective. And I feel like, maybe it's like for a hobby
I
language,
mean,
like security is kind of getting ahead of ourselves, but like, um, it's one of
e
those things that's like, if you're going to invite self-modifying code, I feel like you usually have to have like a really good reason. Like, it's
even
like,
even
oh,
C and
self-modifying code is like,
even C and C++ have self-modifying code though. Like as an
uh,
example, it's called the
uh,
dynamic linker. The dynamic linker does
Oh,
relocation
it does.
patching when the program starts, and that involves writing to code regions. It might mark the code
It,
as not executable when it's
yes, but
done.
your dynamic linker has that as part of its security frontier, and it is one of the most like security hardened, security critical components of your entire operating system. And, whereas
people have
any
hacked it.
program that you emit that has a static variable is going to have the exact same, frontier of possible stuff it could do,
You know
which
what?
is,
I'm with your
Yeah, I
original.
think it's worth paying that price if you're buying Git class for name. Git class for name is very valuable.
Yes. Well, there's that too. I'm sorry. I was just thinking it's just premature for Ryan to worry about it. He at first has to have a million pieces of code that people really care to hack, and he doesn't. So no worries, Ryan. I claim charge ahead.
Well, I guess I
Cross that
was
bridge when you get there.
my kind of thought here is like, okay, do I make this a where's the overhead though? Like, because I know both of these approaches work, right? One is
I
patching and one
claim
is
I claim that the no ops will always be cheaper because modern hardware just eats that so fast. Whereas
well,
an unported load,
I actually can't do a no-op because of the way LLVM patching works. Like I have to have, in order
oh,
to make something patchable, I have to have a non-inline function call. So my
right?
question is the cost of a empty function call higher than the cost of an atomic acquire load? That's kind of my
You're
question.
saying
Like
I have a
probably,
call
I think the
return and an
call is probably
empty call
smaller.
return. An empty call return or a memory reference order load.
basically.
because you're living with LLVM's limitations.
Hmm.
Then I don't know. I probably the load is cheaper than
I
the
don't
call
know.
return. Both of
I
the
mean,
call return
calls are
get you a
just cheap.
pipeline.
All you're doing is shuffling around some buffered, I don't know, maybe saved stuff on the stack, and then like it's probably a direct call, and so like
Yeah,
maybe it's really, really cheap.
assuming it's a direct call, it's a pair of highly predicted jumps in the instruction pipeline. Assuming the return is entirely predicted, then maybe it just flows through almost as fast as a no-op. I and maybe it just varies by chip architecture, and you'll never guess which one.
I think the real answer I would propose is somehow escape LVM's limitations. Like, it's not that hard to do. There's a lot of stuff you can do practically with LLVM. You just have to maybe bring on some burden of, oh, I'll implement this for each architecture or something like that. Like, some like make some inline assembly, somehow hack the LLVM code gen so you like figure out the address of it. Like, I don't know, you have a lot of options, right? Like all you really need to do is emit like a little instruction, like probably one of like a handful of instructions to patch this out. And once you do that, it's like, yeah, absolutely. If you can patch, then like absolutely it'll win. Um, I would just, yeah, I mean, so
Right.
obviously for like prototyping purposes, it could start as a call or something. But I think I would imagine there's probably reasonable likelihood you could do something a little bit evil with LVM and make it just actually patch it to whatever you want. It's not that hard to hack the LVM JIT.
Yeah, I don't know. I don't really want to do anything too crazy because it'll block inlining optimizations, especially inline assembly is really dangerous for like
I
making
mean,
it
but
where
you don't
you're
want to inline
either.
this, right? Like you don't want to have to inline the all of the synchronization stuff or the like call to like or the like patchable call to init something should specifically not be inlined, right? Like in your current hypothesis, like you
Yeah,
know,
but the
you
the actual like so we have this non-inlineable function call, but then we can have the inline access to the variable and stuff.
Where are you hacking you down here? No, no, that's me. Fine. You
are
want
you
the
saying like does LVM block inlining if you have any inline assembly in the function?
It can do a lot of things that will
No,
prevent
does it have like
like
scheduling limits across the assembly, but
yeah,
not
that one
yeah.
it can, but you can technically tell it to get finicky with those things. It's really weird though.
Hmm.
Yeah, I think by default, technically, there's so the way that it works is that it has a bunch of flags that you can toggle on and off to do with even like whether or not you think that the inline assembly should be modifying memory. If it doesn't think that it can modify memory, it's actually totally allowed to like order loads and stores around it, which is very rare, but people do use it sometimes.
I
And you
mean,
can also make non-volatile inline assembly.
yeah, like if you have these options, then I feel like I don't know. I guess like I'm liking the personal experience with exactly what LVM lets you do, but like if I'm thinking of like a JIT patch point or something, mostly this is just like it comes down to what effects do you specify this patch point has, right? Like I have to imagine there's some maybe limited equivalent of that allows you to like not completely pessimize all your optimizations from having a little bit of inline assembly. Like LVM is a pretty smart effects model, right? Um, but that's kind of a guess because I don't know LVM that much.
I only know these things because of like OS stuff with Clang, and then running into like what are you allowed and not allowed to do in that context. And the answer is quite a lot actually. Or like you're allowed to do a lot.
Hmm. This is yeah, okay. This is dealing with LLVM adding patchable points. The thing that I would think you'd have trouble with is threading the patchable point out of LLVM's, where he landed it in the actual code space so you could have your slow path patch it. Go find it. Right. After post optimization, post unrolling, I cloned the code 15 times because I unrolled or I inlined it or whatever. It's all around. Where are all those patch points? How does LLVM track them that you can get it back later? Is it doable?
You can
Do you
just
even have
ask it
to?
for the IR and then say like, hey, where did you put all the inline assembly blocks? And if you tag them yourself, you
So
can just
tag in the IR, track
yeah,
through the IR, and then have something read through the IR afterwards. Put it in a table so at runtime, the runtime can go read the table and do the patch.
yeah.
Can you just do it in the slow path? So every time you hit the slow path, oh, it's already loaded. I'll get my return
Yeah, you have to go
location
get your
from the
return
call stack
address,
and then patch.
and the shape of the
And then,
code from the return address has to be the same that you can find all the parts you need to patch. The other piece of patching, by the way, is can you atomically patch in the face of racing threads, which generally means using a CAS to patch, which generally means that the scheduler has to not have an x86 op span a cache line boundary. So if I have a call op and I've called into the slow path, I'm going to patch the call op to be a no op and just get rid of it. But it's a 5 bytes, spans a cache line boundary. I can't atomically wipe it to no ops in one go. So if I nop half of it, then somebody comes along and sees the other half as ops, right? And they get confused. It makes for a terrible debugging series that takes forever to find, speaking
oh,
from
you're not
that
patch. So you're not
experience.
going to patch it with the jump to jump the call.
Yeah, so now you have this funny thing where I'll put a jump here, but the jump is 2 bytes, but the first byte is on the edge of the boundary, so I can't put an atomic jump in. I can't write a normal write of 2 bytes that spans cache line, so the target of the jump is messed up as well. So there are some games you
Yeah,
play
you've
that
got to get
Hotspot
your
totally plays
alignment
some of these
right.
games, by the way. We demand the no ops to force the alignment, but then we'll throw down a 2 byte jump and even we have 2 byte jumps to itself. Just make this thread spin for a moment, and I'll finish the patch elsewhere, and then I'll unpatch the no op to spin to let it go. I think that patch eventually got taken out as being too clunky, but there were definitely various attempts to try to patch, but most of them started out with I'll assume it didn't patch across a cache line. That was buggy, but with low frequency fails. Then it was the code generation for this WAD includes internal no ops according to alignment that we had to go tell the code scheduler what the how to honor that alignment, and then we could patch it.
I will say,
It's
when I said earlier that inviting self-modifying code and patching is a high expense feature, these kinds of things are kind of what I'm talking about. Like,
Yeah.
I mean, Cliff, you're right that it should be like you solve it once, or maybe you solve it like half a dozen times as you find ensuingly complicated bugs.
x86
But
has bonus extra solving issues, but Java versus JavaScript implementations should have been able to share the same
oh
patching
yeah,
implementation.
I don't know what the lineage of our patching stuff in RVM was,
I'm
but I
sure it
know
wasn't
like
anything
a
from.
fair amount of our stuff is like inspired by various JVMs and stuff. Anyway, there's a very nice lineage from like Java VMs into like V8 and JSC. Um,
Oh, there is. Okay.
I think there's some history. Like I think a lot of the I don't really know that much.
There's
I
a
heard
lot
some
of
of the very early
easily
like V8 people were
inspired
all
by.
hotspotters.
Yeah, these guys solved this, so we can solve it, and then it's the same hack for both of them.
Yeah.
Fine, but they didn't actually copy code, or I don't know. They did. Okay.
Um, but doing all this in LLVM seems like I don't know, bit of a boondoggle. But you could probably make it work. Like, it's like you could probably try to do some code alignment, but I don't know if LVM actually supports that. In a JIT, it'd be very easy. You can just say like, oh, I want to do a patchable thing, and I control my assembler, so I'll just align it, and that
Right.
makes a lot of things easier. But LVM, who knows? Because you've got like all the like crazy instruction tables. Um,
Yeah, because of the inline assembly, the reason why it's so kooky and great and amazing and weird is because GCCs is really weird, and GCCs is really weird because they just let you copy paste into the assembler because GCC's like pipeline doesn't think about like it does not just logically but literally spit out assembly to an assembler like internally, and so because of that the inline assembler is allowed to write all the directives that the GNU assembler is able to do because you can just copy paste in there, including comments. You can copy paste comments into the like GNU through C into the GNU assembler.
So you could put
LLVM needs to copy the logic of that, and so in which case they have support for basically all of the GNU directives. in their inline
With
assembly.
alignment directives.
Yeah, you could
Okay.
say like, hey, align. Not, you could even ask it to not align.
That's what I meant, not align. Not
Yeah,
align. Yeah, yeah.
it's got directives for that because GNU has
Okay.
them, and they
The
need
Java
access.
hotspot, the hotspot has knob alignment for the patchable points as a
Yeah,
thing, but it's not through the assembler. Yeah.
But I mean, if you have that, then maybe it's not that bad. I don't know.
If you're aware of all the issues, then they're all solvable. They're not, none of them are rocket science by themselves. There's a lot of bit fiddly things, but no real rocket science. You just have to be aware of all the weird failure modes that. And as soon as you go to a fixed 4 byte word instruction op, like a RISC or an ARM, like a lot of the real nightmare scenarios just go away. I can always have a load compare branch slow path thing. I can arrange that. I'll put a jump at the first one. The load becomes a jump of unconditional over the crap in the middle. Then I'll knock the crap in the middle out, and then I'll knock the load out, and no one will ever see anything other than an executable that's totally sane and all that kind of stuff. Like it's 4 byte aligned ops. It's all easy.
I mean, there are definitely some similar, or I guess similar but different issues. Like, if you want to do like a patchable indirect call somewhere, right? It's 16 bytes to materialize an arbitrary address, or I think 12, just because your immediates are smaller.
Yeah.
Um, so there's some
Yeah.
trickiness.
On an
I mean,
ARM, on a
I
RISC.
think ARM64 is capable of doing that, but I think
Okay.
like ARM v7 doesn't have big enough atomics to do that easily. But I guess ARM v7 has smaller addresses anyway, so maybe that's okay.
Yeah, I'm
Um,
trying to think. So in the x86 at Sun, we only 30-bit code addresses forever and a day because only 32-bit chips for a long time. And we had the instructions x86 load 32 bits. It was all sane. All the other risks were doing 2 ops to load a 32-bit immediate. And if you had a patchable code address, it was kind of a bitch to make that work, including halting people just a little while you finish the patch out or forcing slow path until it could be whatever. The fix I did later at Azul was to load all 32-bit patchable immediates, so code constants, GC constants, string constants, whatever, put them in a table, and you loaded from a table entry, and then the table itself was just a big array, and you didn't have any patching to do, or you had totally perfectly aligned data you could atomically patch in the array. That was, you paid the indirection cost, um, but was all L1 cascading loads. It was all really cheap. And
that's
it's
probably the best, portable solution. I think, like depending on the architecture, there's a lot of like other hacks. Like ARM64 has atomic store and load pair, so you can do a double register atomic loader store, which is pretty
right.
handy. But like RISC-V doesn't have that as far as I'm aware. So they're just things get complicated. I don't know that much about RISC-V atomics in general, so maybe they're also really
Because
different.
no one, not no one, not everyone had double word atomic updates. Mostly people figured out how to work around not having them. Like almost everything you want to do with an atomic update, you can actually get away with one atomic word that's a pointer to something fancy, and you're swapping out for another pointer to something fancy. Code hacking is one of the few places where the 120 bits, the larger atomic update is useful, really. But like double linked list updates are technically require double writes and reads, but you can almost always come up with a data structure that doesn't need it. Kind of a funny deal. But the atomic code address update was a little bit more of a bitch. All right. Our brains are all sad and confused from self-modifying code. Yeah.
Right. That's cool. I will actually have to go here. I got a meeting.
I'm skipping my meeting to do this one. So there you go.
Oh, see you guys.
And my goal this weekend is to get Claude code on simple running. Of course, I have all kinds of other real life events happening at the same time, so we'll see how far I get. But I definitely want to get and AI. I say Claude Code. I think I've got a highest end pro. I know somebody who works at OpenAI. I think it's OpenAI, and yeah, it's OpenAI. And I have the highest end version of whatever they're doing available to me, and I want to get that running on simple and see if it makes my life easier or I can get more done on the weekend when I'm not doing other things. Fine. We have guests out of town and I'll have guests again, and then I'm traveling in a couple weeks, and then I'm still hacking on simple. I want it to be done, or at least to get past the point where I can do a static, a separate compilation, so I can do a library. That's a long-term goal. Is to well, it's been month and a half, separate compilation, so I can compile in a standard lib and have no include files. So I guess that's the other piece of that. Ahead of time compilation strategy, not a JITted strategy, no include files, which requires me to compile things and put type system stuff in the .os. And so much of it is working. Fine. There's my simple update.
I know we
All right.
talked a little bit, I think, about your like object file implementation last week, but on a language level, like how do your libraries work? Do you have like a single file as a module? Do you have some sort of multi-file notion of libraries? Um,
Yeah, I have a hierarchy. Let's see if I can. I mean, I have the module uses a directory structure. Let me go see if I can pull up Emacs pointing at the correct place here. Give me an Emacs moment while I
Good luck.
exactly sort out source main. It's not Java, source main simple. And here is the standard library as it sits. And many things are turned off. Okay, no, but this is like not not ludicrous. Let me do the share thing. Okay, Zoom, stop it. Now start it. Da 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 da. Okay. And Zoom's going to grab the keyboard, let go of the keyboard. All right. I want to say Control X plus, and Zoom grabs it, stops the Zoom. Okay, so the start of the standard library is source main SMP, source main simple. The first one is simp. This is uh, this is go libc. There exists an IO. So this will turn into a struct who has fields libc and a field IO and a field parse array I64 as in the middle of doing something. There's a scan. Where the hell scan come from? I'll leave it at 4 byte indent. I should fix that. Okay. Scan has other things. Get a new array of yada, yada, yada. So where are those? So if you're a module entry, then everything in you gets run and initialized. So these variables, this is code. It executes like you would execute just Python, just straight through run it, and it just assigns these variables. So it looks up libc and assigns whatever it finds in the variable called libc, which is the field libc in the struct. So this is a definition of a struct called simple or called sys. It has three fields: libc, io, parse array. The execution of it just loads some variable. Where the hell does this come from?
If
Into
a reminder may want to make your font size much larger. I'm on a 30 something inches screen and I can barely read this. Thank you.
no. Every time I open a file up, it will be the default, and I have to grow it. And then Zoom wants to grab me growing and try to grow his like chat menu for me, but nothing for you.
Yeah,
All right.
and it's on YouTube, the compression would kill that font size for everyone.
Yeah, right. Okay. So hopefully this is readable. But the semantics are there. This is a file, sys.simple. The semantics are when you mention sys somewhere, you will get the class init structure, which will have three fields: libc, io, parse array. They're defined that these values come from these variables, which come from somewhere. I'll show you in a second. Or this one is a function I've declared in the spot. So that's a function start. There, it's got the arrow, and there's a function body that gets assigned into that variable. Okay, where did this like libc and io come from? Well, in the same directory next to a sys the sys guy. So any module head piece, including recursively indefinitely, if you have a directory of the same name, then it is the same namespace. And now I have a bunch of other simples in here who all are prefixed with sys dot whatever it's going to be. So here is IO, which has a shortcut for print and standard in, and the print guy goes to libc write. Okay, where's libc? I was just using it a moment. Here's libc write. Libc write is just bindings to libc. So it has the syntax on the end of quote C quote. But the module semantics are go look at I would say sys.libc, and sys would be provided into my injected namespace by the command line options where I say where my standard library is. So however you get libc when you compile a C program. Um, from sys, I would say sys.libc, which would give me this set of bindings. And then, I have an array, which is a array helper like Java arrays. It's just array copy. And I'll have it. I mean, I don't really have a libc. I mean, I'm sorry, I don't have a standard library of any merit here. Here's an array of bytes that's growable. So it's a little different. Oh, I have mid cleanup of this one. That's why. So there's an array U8. I no longer need this one because I'm in a file array U8. So now I have a doubly nested array U8. This would be sys.array U8.array U8. I need to get rid of the outer structure. But it's an array that's a vector of bytes, and it has a length and a buff, and there's a hidden grow field. So the underscore on the name grow means it's private, which just doubles the array size until you fit. And then there's add a character and add an array and undo, which just moves the length pointer back, and convert the field, some ASCII number into bytes in the field. So write a number out, things like that. Um, So here's like a main called from bubble sort. So there's no pound includes in here. I got sys from the command line from the compile itself. It's the default. Whenever you installed it, you'll tell me where sys is. So I can say in main sys.parse an array of ints. And where do I get that array from? I get it from the string I got by reading standard in. Sys.io.standard in gives me a string. I parse it to an array of ints. So nums here is typed as array of integers, and blow up if I get a null back because you didn't give me the right syntax. And I call my bubble sort. And then I take my array of nums and I call str on it, which gives me a string, which I call write on it to standard out. One is standard out, the FIDX for the file descriptor for standard out. And sort does the obvious bubble sort. But I'm using libraries. Sys.parse array, give me an array of ints, sys.array 64. So this is sort of what standard library usage looks like.
You said you got sys from the command line?
Yeah. So when I compile, yeah.
Is sys like the only package that's like that, or are
Yeah,
all
the only package
dependencies
like that.
Okay, okay.
So you are allowed to put anything you want on the command line. I'm sorry. You're allowed to put anything you want on the command line. Like in Java C, I can say a class path, and here's all my extra
I
jars
see.
and classes. Okay. But sys would be the rt.jar, the default one, right? That you
Okay. Yeah. I think that's
Okay.
cool.
Okay.
The idea of like avoiding like imports and other like
Yeah.
specifiers just by basically saying like here's my project configuration is kind of tempting.
Yeah. And so I don't need an import from Java or a pound include from C because I'm picking these things up from the .o files. So this is the code that does whatever it's going to be. When you build the obs here, no, the project's not currently built, so that's why there's nothing there. Well, so somewhere in my obs directory, I would have an object files for all the source files that got compiled.
Right.
It
I actually had a
compiled.
question about that.
Yeah.
I certainly understand it, like, because it sounds like the object files are still a little bit like work in progress, especially with like, embedding type information.
No,
I was curious to.
they're solid. They're done.
Okay, well then, so my question is basically, um, when you actually get your object file output of this, is it a goal to still use like a system linker? Can you just use a normal linker to build?
Yeah.
I mean, so for one, cool. I like that. I'm also doing similar things. One conundrum I've kind of run into though. And I guess like, I haven't like maybe this is a thing you can run into on a general source level. Do you have any special handling for like unexported symbols? Because I think this is one of the things I've worried about a little bit is if you have if you have all these like nice libraries, right? Like,
Yeah.
obviously most of the functions here are things you probably want to export, like, oh, I've got this type, here's how I add it, here's how I turn it
Yeah.
into a string. But,
Yeah.
If you have like some library with like a big rich inner implementation,
Yeah. The
do you do any
underscore.
hiding?
Yeah.
Okay.
Underscore says it's hidden.
Okay, well that's pretty simple then. I
And I
guess
probably should
henchmaning
go
maybe.
hide, length, and buff for this implementation. Actually, I want buff to be visible but not writable, so I would need to have a read-only version of it.
How do you do that on a binary level? Like, do you do
Oh, I
like
don't
currently
focus
what
in.
I'm doing about this is a little bit gross, which is I basically require that my compiler is able to do internal linking, and so I just don't emit any relocations.
Oh, I see.
Um, do you do
I'm
something
doing.
smarter?
No,
Because
I'm
I feel
doing.
like this is like
No,
high
I'm doing
effort.
this internal
Oh,
linking.
okay, okay.
But it takes no effort for me. I don't know. I'm from scratch for everything here. It just takes no effort.
It's
So
I guess it's fine. It's just like trying to remember actually what problem I ran into it with it. Maybe it wasn't anything too much. I guess in my language, my exports are a little bit less clear, but I have not really wrangled with libraries that much either. So,
so
I'll
here.
figure that out eventually.
Here in the encoding, I lay out all the code from all the calls and everything in the universe. I write them once and count their size. I do an x86 special for jumps. I write a constant pool. I patch relocations, patch local relocations. For the local relocation set, get the start of the op, get something about the dest for the target or whatever, and hand those pieces off to patch, which is specified per op according to her hardware op, according to if it has patchable pieces to it. So I do
Hmm.
internal patching. So this is all like I had that underbar grow as a hidden function. If I chose not to inline it, but I have a call to underbar grow. So let's go look at this. Here is a call to underbar grow. If I choose not to inline it, then I have a call to underbar grow
Yeah, yeah.
internally.
You
I
have some
can,
kind of internal relocation.
that was it. I just patched it right
Yep.
there. That was the patch.
Um,
Done.
so I, I guess this is a good answer to my question because I think I was unsure if this kind of internal linking was like a smart thing to do because I think like theoretically there's like I don't know there's like local symbols and things like that in object files, but I feel like I was also thinking kind of along the lines of it's best if you just don't emit them in the final binary at all.
I'm
So
not right. I'm not omitting
this
them.
kind of local relocation is pretty good. I guess other question, probably the reason I'm assuming this is hard is just because I think my relocator is kind of buggy, but that's a skill issue on my part. Do you do any branch compression, or is it just a
Yeah.
pretty straightforward patch?
No, that's what we go find this guy. Here's my top level. This is the encoding driver for the back end. Compact
Uh-huh.
short form. That's your branch encoding. Compact
Ah,
short
okay.
form. Let's go find it. Here it is. It's ugly, but it's all this one file. So I mean, one function, right? So this is go get a local array at the start of every opcode, which really just walks through and asks each opcode, how big are you? And makes a rolling sum. Now I have the start of them all. Then I have a slide. Oh God. And I have a repeat until I quit sliding shit. And I start with all short jumps and read the comment there. Check the size of short
Mhm.
jumps, adjust the block. If I need to make it go longer, stretch other blocks and go pass again. Block.
Oh, interesting. So you actually do this over the IR? Like the IR knows how big it'll be in the binary?
Um, I only ever
Like,
have an IR. The IR is only ever sea of nodes, and I've replaced the nodes with hardware nodes, the
uh-huh.
the idealized nodes with x86 hardware nodes. So I can
Yeah,
ask
right.
questions. Okay.
No, I guess it's been a while since I've seen a compiler that operated like that, but I guess I remember working with like GraalVM at one point, and I think they do something similar. It does
Okay.
make a lot of things easier. I just feel like
I
it
ne
is also high effort to have to specify not only will I have this like these x86 instructions, but also like I'll have this extra representation where I know how big they are and everything. Which again, this
that's
is probably like
I
a
find it
skill issue on
particularly
my part.
useful.
it's not a lot
Yeah,
of work.
yeah.
I
I
mean,
think it's a lot easier than having two separate IRs.
yeah. I claim it's a lot easier than two separate IRs. Yeah.
Yeah.
Currently, what I do is everything is done basically over the binary, and so I just have essentially like an in-memory object file, and so I have a binary and I have a list of relocations, and the relocations store their size and things like that, which has been pretty efficient, I think, but it's definitely not as flexible. I've been trying to dodge the like especially for multiple architectures, it gets to be like a lot of just copying in tables, which I've been trying to avoid so far.
Well,
But
only
okay, if you actually know how big the opcode is, then yeah, that
yeah,
makes a lot
no,
of
right.
sense.
I am emitting. I am the assembler as well. I took this straight from what I was doing with C2, except I cleaned up the path. So it's actually not very much code. But here we go. Score something in CodeGen. No, go to nodes, go to CPU, go to x86, which is the ugly one. Here is all the things in the universe for x86. Here's a compare as a sample dude. He says, I'm a compare. I have fun names. I take default register masks for things. I can be cloned, whether or not I care to. Okay, there's an encoding. Go get your encoding for the register value for your two things to compare, input one, input two. Put down a rex byte according to the size of the registers, a three baker, a mod RM of a direct
Yeah,
mode
yeah.
destined source. Oh, there's
When
a
you when
pretty print.
you when the internal linker asks how big an opcode is, does it actually like for this encoding, does it like pass in a like encoder object and then figure out how many bytes were written or something like that? Like how do you actually figure out the
Basically, but it's
size?
a big bulk pass, so that goes back to that
Hmm.
encoder object, and he goes up to let's see here, was it the find it shortcut here? This guy, write encodings. Okay, let's go look write encodings. So write encoding says for all blocks, for all things, uh, go for outputs, go write, which records your bit's size into op
Yeah,
struct,
yeah.
then encode it. Now get your length recorded as size minus the start of things.
Yeah, I think that all makes sense. I guess I've done some similar tricks from time to time with like looking at my internal buffer. I still do my own assembly, but I don't have any data representation of the individual instructions. But
Okay,
yeah, this is clever. Or I mean,
enough maybe, hopefully.
I think it's
But
like it, it it's
it
it's
means
probably effort that's
I'm
worth
not picking up
doing,
anyone
and maybe
else's
I should do
tools.
that.
This is my standalone compiler. I don't have any other
Yeah,
tools. I'm
yeah.
not picking up an assembler. I'm not picking up a
Oh
linker.
yeah, yeah. No, I mean, I very much appreciate that. Like I said, I wrote my own assembler for my work, but it's essentially just like a functional like macro assembler, right? Like it's just, I have a
Right.
function that's like emit this thing, but I don't have a data representation of here's an x86 add that I can introspect on.
Oh,
Um,
I don't really have that, what you just said. What I have, if I go back to that comp,
well, you could do like an instance of, right? You could say like, oh,
I make
is
a
this
new
machine
instance.
node a
Oh, yeah, I do make a new instance. Yeah, I do make a new instance. Oh, I see what you're saying. No, you're right. I make a new instance of a comp x86.
yeah.
That's in
Well, and
in
you still have your control flow graph and everything too, right? Which is
it's
still
all sea of nodes, so they're all just nodes in the same
or
giant
yeah,
graph.
yeah. You still have an IR graph.
Yeah, and the IR nodes have been swapped for an idealized compare with a compare x86.
Yeah, yeah.
Okay. And then this extends Mach node concrete, gives me a bunch of free calls. So this is what I know about the ops I have is the Mach concrete. Because I don't know other things are just whatever things floating around. And all I know out of a Mach concrete is I can has a label and he has a pretty printer. And I have a Mach node, which has me a few other things. Oh, Mach node is the one I was looking for. This is the guy who says something about you. I know that you belong to a machine type, which is ARM or RISC. There are some hooks for things. There's a bunch of get your registers for your inputs and outputs, and
Yeah,
kills,
yeah.
kill registers. Are you a to address? Was x86 special generally? There's a few ARM ones that are to address. Can I swap your arguments? Register allocator loves these. Can I clone you cheaply? That's a register allocator. How do I make a copy of a cheap instruction? But actually, I use this in a lot of places. How do I encode you? How do I get you in a pretty assembly readable version and the opcode hook? So
Have
I,
you
I
have you looked at the performance of this, like in terms of like assembler throughput?
C2 does this for hotspot and it's fast. Yeah. I
Okay. I
never I
think
never
that
go in and out of a text form. So that's already I don't have to read and write text, assembly
mhm.
text. So it's fast there. I haven't done big profiling on the simple implementation, and I definitely made decisions on simple that were slower for the naive compiler writer to read easier.
Which I
Um,
think is, I think like that's a very defensible thing. I think it's, this is like a dream kind of type to have as like a compiler writer to be like, oh, I can look at my, I can actually look at my low level instructions and ask all these things about them and figure out their
I'd
registers and
have to
stuff
bring up the
versus
debugger,
some other
but
separate thing.
I can stop the compilation at the encoding phase and hover the
Yeah, yeah.
mouse, and out pops the assembly, including how it's sorted and the register allocation if it's done. All that things just pop out when you're debugging and looking at shit.
It
Yeah.
is very nice. I would like to see I am kind of curious what the profiling looks like for something like this. I think, there's sort of this tempting idea of like, well, theoretically, if you can avoid all the objects and you can avoid all the method calls and things, like maybe it goes a lot faster. But I have actually found like, despite my initial plans of like, oh, well, if I use this like really bare bones procedural assembler, it'll be really fast. Like the actual process of lowering is still just kind of the dominant cost, and like actually
Oh, really?
creating the assembly and computing mod RM and stuff like that like dominates, seemingly a lot.
I
I
would.
mean, it's not, expensive, but it's
But
compared
here's
to
my
like
phases.
allocating a little thing.
I suspect I'm fairly more expensive than I would like in parse. Um, I would not imagine coding. So if I go to C2, which heavily optimized and
Hmm.
got the parse was vastly cheaper because it wasn't a real language, it was bytecodes. If I go to C2, still parse was like 40% because
Interesting.
inlining and some poor decisions about inlining that went through. And the IR has this giant inflation from bytecodes because it has safety checks got inflated that immediately wiped out.
Huh.
But the cost of inflating and then deflating the safety checks was still a big chunk.
That's kind of really surprising, actually. Like I would expect, like, especially if you do other optimization passes, like, I don't know, I'm trying to think of like what
Oops,
are,
we're 20%. So
huh.
opto type check doesn't count. And in here where I highlighted, C2 would have loop ops. That was like 20%.
Hmm.
And then encoding was hardly anything. Instruction selection. Well, this piece of encoding is actually me dumping the graph IR. Instruction selection was hardly anything at all. Local scheduling was not very much. Register allocation was 30 to 40% more.
Yeah, I would
This is the
figure.
encoding write phase at the end.
I'm definitely surprised parsing is high. Like, I guess I don't know. I think like JS engine counterpart, like our top tier, we would spend like 30-40% of time in regalloc. We would do,
Yeah,
maybe
30,
like
40% regallic.
I think
But parsing was
gosh, what
much
actually took a lot more
higher.
time? I think we would take like maybe 5 to 10% for like our other big passes, like instruction selection and things like that. And then
Okay.
you know, I'm trying to remember what actually took the most time. I think maybe lowering took a lot more than actually
Yeah.
parsing. I mean, we didn't technically parse because we had a different, we didn't actually have to parse an IR from like a bytecode or something. But the equivalent parsing of like JavaScript or something was like,
I think
I don't know,
lowering is
like
instruction select here. It's not, there's
1% of total runtime for a JS heavy benchmark. Like our parsing pretty rapidly went away, I think.
Yeah,
Um,
okay. I don't know why it kept getting bigger because we kept adding weird shit because we had inlining done in the wrong place. So you had all the inlining heuristics were running during parse.
oh, okay. Then maybe that would explain it. Because I feel like inlining is also like, I mean, like generally my understanding is I think the stuff that takes the longest time is really the stuff that creates the biggest input. And so like,
Yeah,
whenever I look at regalloc, right, it's like
yeah.
it's not that regalloc is that slow, it's that it has to touch every live range
E-
basically, which is just you have so
Yeah.
many of them.
Yep,
But if
yep.
you're doing inlining and you're, doing all the
I'm doing
node
inlining
allocations.
in the parser in
Yeah,
C2.
yeah.
In simple, inlining is done all the time as part of normal peepholes.
That's good. We had a parsing based inliner in one of our tiers in JSC, and I think it was it's not necessarily a bad solution, but I think it's a little bit more inscrutable than having like an extra pass that's like, no, here's exactly like, before inlining, after inlining, all this stuff.
Mm.
Doing
Yeah,
it
yeah.
as you go parsing wise is kind of a pain.
Inlining is a heuristic that needs constant tweaking, which means visibility, for which you
Yeah.
need to have a lot of extra information, printouts and shit to help you decide that your heuristic is good or bad or ugly or whatever. Inlining is one of those things that needs, it's like I do for rich allocation. I need a lot of printing heuristics around, I'm sorry, you need a lot of fancy prints in register allocation to help the heuristics on spilling. And so I have a bunch of extra printouts there. Here I was just trying to show on the screen the overhead for doing instruction selection, which is essentially I got an identity map comes in that's node to node, which means it just does an equals check and not a dot equals, so equal equals. But I run through the graph, I walk all the nodes, do a map get. If you've already done, you're done. If not, I recursively walk through your inputs, and then I do under mock.instruction selection. Call instruction select. That turns into the x86. Let me go here. It turns into this guy, which this is the giant file of what things happen on an x86, which is bigger than all the rest. Turns into this switch statement. I take an IR node on the left, and I get an x86 flavored on the right. That's the instruction selection. It's really
That's
dumb.
pretty cute. That's good. That's so clean.
There you go. There are a little bit of fancy places. Add will do load effective address breakdowns. So when I say I found an add, I greedily say, oh,
Hmm.
is it an add of a load? Well, maybe I want an add mem x86. And is the right-hand side a constant? Is the constant respectable? Maybe I want to register it. Maybe I want to say I want to do an under Leah. Well, I'll go find out what under Leah does. Maybe it needs to do a shift scale add thing. Maybe it's just an add of an immediate. And then under Leah here will be do a little bit more with shift scale adds and just report back, oh, I couldn't do it, or oh, I'm going to do the x86 LEA versus an add with whatever other bits. So in each of the breakouts from the big switch, it's all greedy. So somebody says, and I can fold in some extra things. So a multiply float does nothing, but a mul op has some special extra things he's doing because he's got a subroutine here for the mul. So if I look at mul, it won't be much, that's for sure. Yeah, he says it's a mul I or a mul reg. But that's it. C2 did a lot of really fancy things with what they call Burge pattern matching, tree pattern matching to get a optimal, whatever that meant, instruction selection. And the answer, of course, is horseshoes and hand grenades and nuclear bombs. Close is close enough. No need to be perfect. Be simple. And all the out of order, wide issue, blah, blah, blah things on the planet will eat up all the little tiny bits you get for having less than perfect instruction ops. So
Yeah, I was gonna ask, do you do anything earlier than this? Like, do you have like a higher level like strength reduction phase or something to do other kinds of node
no,
pattern matches?
that's
Or
CodeGen does all the optimizations that happen, and that's mostly those are all those peepholes. So where's my big CodeGen pass here? But those are peepholes. Strength reductions of people.
right, yeah. So I was curious if you're still doing those.
Yeah, that's all done. Opto does them sort of officially to the completion, but the parser does them all the time as he parses. He calls peephole. So if you do
Interesting.
multiply by two, when you go to the parser, he'll do a peephole on that, right? So parser somewhere
Hmm.
has a mul node, so new mul node, and a font, blah blah blah. So someone says, "Oh, go make a new mul node." And what's the left and the right hand side? Well, eventually he calls peep. Okay, that turns into people on a mul node. Node, mul, node. And here he says, "Oh, call idealize on the mul node." That the people says, "Go to the idealize thing." Swap constants so they come on the right-hand side. So you have a canonicalized form. Multiply by a constant. Oh, you're multiplying by one? You fold up, become left-hand side. You're multiplying by zero. Oh, become a zero. Oh, you have one bit, become a shift. Oh, you have some other kind of crazy, stupid things, a few patterns I do. Then I skip all the rest.
Hmm.
Then I'm done. Right? There's another one down here. This is I share the phi function where I have a multiply of two different phis who have different constants. And I can push the multiply up and get the constants folded on the other side of the phis or something. So there's some more things.
Uh-huh.
But basically, as you make a thing in the parser, you immediately peephole it. And that counts for things that look like strength reduction.
Yeah, that makes sense. I think I mean I've never seen anyone do people like right on the parsing stream before, but I think it makes some sense. I mean, from the like I guess
Does
close is
it?
close enough philosophy, like,
You
you
do
know,
Java, C2, parse it right on peephole's right on the parse stream.
I mean
And
theoretically like, like I guess like if you're also doing your inlining as you do this, then that probably
Inlining,
enables
yeah,
a lot
Even if
more.
you're
inlining.
not doing inlining at the same time, like it's still kind of useful to remove all the like random little algebraic wranglings. Sometimes
Oh yeah,
people
I mean,
write
if you can
things
just
like if
decrease your
x
code
equals
size.
0 or if x is not equal 0, and like it's a stylistic thing. But if you can remove it
Mhm.
early, you can save on cache.
No, yeah, I mean, that is definitely useful. I'm thinking mostly just like in terms of, actual code quality. Like, I would imagine you probably want to do, I mean, I don't know. I guess I don't know what you do for like mem2reg or anything like that. Like
I'm sorry, say
anything
that.
for load, like memory to register optimization. Like if you have like a
Ah,
load or something and
yeah,
you put that in
yes.
like a register.
That would
Um,
be right. So for me, that turns into memory ops in the sea of nodes memory phase, which I do load, store back to back. This is inlining, which we as an idealized call, which means it's done during parse and everywhere. Idealized is
mhm.
called all over the place. Mem ops for load mem store elimination totally happen here, and the same story
I
happens all the time during parsing.
But do you do people
something
after
potentially
eliminating
being glossed
memory?
over is in C, for instance, or in C++, variables when you're going through, let's say, the Clang pipeline or a lot of traditional like sort of LLVM based compilers, you'll start off with variables being memory locations that you load and store to. Cliff is not doing that. Cliff is starting with SSA form for the
Oh
variable.
yeah. I mean, I figured, but you still can get like if
Load
you ever
after
have
store.
something that does touch like a lot of memory, but then you later figure out, oh, I can like escape analyze this and actually turn it into like, and then I can like, scalar replace it, and then all those
Right, that's
scalars maybe I
this.
can do my own peepholes on or something like
Literally, you were
that.
looking at it. This does
Um,
that stuff. You're saying I have all these things I would touch, whatever. Invariably, they turn into I have a load, I have a store. Oh, the load comes after the store. It's the same. I just don't need to do the load. Then later I said the store is dead. I don't need to do the store either. There's a different one for store goes dead.
do you do any I guess so you have just like strictly equivalent. I guess is it type-based aliasing or
Yeah, yeah, type-based aliasing.
is I guess looking at this, it looks like it's exactly the same object. So you don't do any like, you know, I guess if you're doing store elimination, you don't actually need to do aliasing as much. Or if you had aliasing, it would just
You have
pessimize it.
type-based aliasing. You have perfect alias information in the graph. That is, as you modify the graph, it remains perfectly correct every step of the way, and it lets you do any load after store after store, all those kind of things to fold up sort of as a tiny peephole. The
I mean, I guess
type-based
I'm looking
aliasing
at
is
like,
really strong.
it seems like I mean, like doing the store elimination specifically seems like it would require the like pointer equals st dot pointer that you have here, right? Like,
This is a loading from the exact same object. Store does something similar, and he requires something equivalently strong.
mhm.
I do fancy stuff here. This is me cleaning off control edges, so make the store not control dependent, so it moves around. And then I have a fancy call that says I can walk through any count of amounts of memory ops. Where's my store after store? Simple store after store on same address. I
Mhm.
got my memory ops a store, my pointer and my offset's the same, and my pointer's valid. Then right here, set def, my store, his memory input, my memory input becomes my input's memory input, which strips out the last use of the input, and he goes dead. So this is a store after store elimination.
Does simple as a source language have like address of? Do you have
No,
like interior pointers?
no, no.
Okay, then
I
then
might,
yeah, I think this makes that a lot easier. Um,
yeah, no. It's
the,
because I'm going for that particular,
yeah, yeah, yeah.
model. Yeah. Now, having said that, I know what I would do to get the effect that you're looking for, and I would still keep my type-based aliasing
Oh
and
yeah, you could
allow.
like you would have type-based aliasing, but you would still have to you would have to prove, like here's my address of or something, and I can prove somehow that they're exactly the same object. Like you need the same strong guarantee.
That's what this is, right?
Yeah, yeah. I think the like I'm a little envious because I imagine this works like very well. But then like
Java's
my
been using
language,
it for
everything is just
25 years. It works
oh yeah,
great.
yeah, yeah. But like
It's
my
not.
language is a little closer to like C or something like that is like littered with address of just everywhere, and
It's
so
not
that
the
all has to get
Yeah,
address of.
eliminated.
I have a solution for that as somebody who does the C side of things. So
What's your
when it
trick?
comes to like weirder objects, what I usually do, so I've got this like congealed thing called the memory pass, which does the fancier forms of load and store elimination. But more importantly, it also does the escape analysis to do with like, or at least like some flavors of escape analysis to do with like, hey, if I've got a local variable that cannot be fit into a scalar, so it doesn't go into SSA form, if I know it doesn't escape and I can always track the address, I can separate that allocation and split the memory address, or like the memory operations, from the rest of the memory graph.
Yeah.
And then by doing that, then the load elimination can start to spot things that it wasn't able to before, because now it knows, well, even though the allocation is technically like it is a real allocation, I know that it doesn't interfere with other allocations.
Yeah, that is handy. I think, if you can actually prove that, especially if you can prove it like easily, I think it's that's one of those like it really makes sense as like an early on kind of thing. Like here's a trait of my input that I just know basically statically, like, oh, I just never actually take the address of this thing or something like that. And I never pass it to something weird.
I have a
I've been thinking very defensively about my compiler backend because I think it is actually going to be extremely common that you, at least in your source, like especially before inlining, like take the address of something and pass it to some unknown procedure. I mean, probably not an unknown procedure, but procedure that needs to be inlined first. And so, there's been some complexity. Just, I
Yasser
still have to
actually,
reason through exactly how I deal with that. But
David, be aware that Yasser just dropped accidentally and is
Yeah.
trying to come back in.
Here you go.
okay.
Sorry, I missed what you said.
Oh, I think like it makes a lot of sense that this kind of like escape analysis, whenever you can do it, you probably should, and it's like a good like preliminary, like as you're initially loading the IR, just like make your input nicer. I think in my language it is going to be extremely common to take the address of stuff and pass it into functions, and so like there's sort of like some phase ordering. Like I'm going to need to do inlining first, probably, and then even then, like some of those address hubs are going to need to be eliminated. So some of my compiler, some of my specific compiler.
Like some interprocedural alias analysis stuff. It gets complicated. I haven't gotten around to that yet, but I would like to, because
I
in
have some
C,
basic
I have like
aliasing.
easily the worst case.
I think it's not going to be too expensive. I do actually have like a work in progress, like super buggy, honestly, but like sort of a basic, like I'm just calling it effects right now because I want to use my alias classes for both like effect analysis, but also like if I have a really strong alias class, then I can prove like, oh, this is exactly this object. I can use that for like load store elimination. I have something like that exists. It's not super slow, but it is just kind of like I'm mostly running into like phase ordering stuff where it's like what like I would like to do this like after inlining, but then maybe I would like to clean up my input before then, or maybe some other phases will invalidate this effect information. So there's just some a little bit of recomputation stuff, and
Gotcha.
I'm saying this right now. I'm waiting for someone to suggest that I switch to C of nodes, which I'm kind of thinking about, but
You can bite my tongue. It's okay.
it's probably not a terrible idea. There's certain things, I guess,
So you're
if I can
leading
broach
yourself to it. I don't have to do anything.
if I can broach it, maybe like one of the things I think that is giving me some resistance for C of nodes is that specifically I have I guess maybe this is not even really a C of nodes issue. Like I think one of the main things is I really value my like very tight like pretty like small memory footprint like representation of my IR, and I have a little bit of consternation about like C of nodes in the form of like
It's really tight if you write it that way. Simple is not on
it probably
purpose.
could be.
Two is really tight.
I guess yes, or have you been doing anything like this? Like, are you using C of nodes for your for
Yeah.
TB?
Yeah, I'm using. I switched over like maybe it's been like a year or two. I think it's been 2 years now. And yeah, my experience with memory usage is keep it small, avoid side structures because you don't need them.
Don't need them.
And then as long as you do that, like a lot of it is just the graph usage lists and things like that, which are things that generally speaking you're going to have in whatever like IR you're going to have if you have an SSA IR.
Yeah, that's cool.
Interesting.
Yeah.
Could you expand on the whole like you don't need side structures? Because I think that's actually one of the specific things that I was thinking.
Yeah.
Like, so obviously from a structural and correctness perspective, like I get that C of nodes, you have like you just embed the extra data in your graph, right?
Name your side structure choice. And that's
I
cool.
think so. So a lot of what I've been doing is like I've invested a fair amount in like very, very compact side structures. And so, for example, when I compute my effects, right, I store like up to two aliasing. I have this like very bespoke representation of an alias class, which can represent like a tiny bit
Okay,
set or a range of
right.
values, and it fits in 64 bits.
Okay,
And
so
so that's kind of
let's cover that
so
one.
so so per node for effects, I have a at most 64 bits, and a lot
Okay.
of nodes can skip this.
So in the land of Sea of Nodes, there are no effects outside of the graph edges. So all your effects are always graph edges. So whatever you do for graph edges, that's your cost for effects. So
So you would need inline like probably a 32-bit index or something,
no,
which
no, no,
I
no,
think
and because it's type-based aliasing, the memory effects are also just an edge in the graph. So that's the main effect here is memory. Let's go look at a
right.
memory edge.
When I say like an index, I mean that would be the ostensible memory compact, edge, right?
No,
Like you
no,
probably can't.
it's just another edge. So here's a load, it's a memo. Let's go to
That's what
memo.
I'm saying is I think, like like I would rather not use a full pointer for my edge, but
I'm
like
using a
it's
full point
probably
for the
32
edge,
bits to store an edge.
but I can make the edge less. So here a memop has an aliasing. That's in simple. C2 doesn't need it. Simple has it just for convenience. The is load is clearly one I don't need. I have a name on a field, which I don't need because I get it out of the alias edge info, and debug bits for late reported errors. All these things C2 doesn't need, doesn't need. So I go from memory edge to type. Memory opus extends type. Type node gives me a constant, and this is like the type. Oops, where do you go here? There you go. The type of the field. Type of the node that is not the runtime, not the compiler's internal analysis type, but an extra constant. Again, they're not needed for C2, and Sea of Nodes is using it as simple as using it for convenience. Like I said, I mean, a bunch of these things here. So it's really a load node comes from a node which has some inputs. If you're C2, there's a count of inputs in 2 bytes, and it had been all your other inputs were 2 bytes as a pointer into one of 65K choices. Now they're 4 bytes into other nodes. So the nodes that go into load, there's a null, there is a memory, there is a pointer. In
I guess
simple, if
so.
I throw another one, sorry, go ahead.
Maybe another point though, to actually compute this, like so your final representation is pretty memory dense because you just have like an edge basically.
Yeah.
I guess one thing is that like if you want to figure out if two nodes interfere, you have to figure out not only if there's an edge between them, but
So when
actually
you
a
say
path, right?
interfere, what do you mean? Let's be more strategic.
So
I'm going to throw this one out too.
so I guess do you so your effect edges, is that something that's basically like a total ordering? Like do you just have like an effect sequence that's like okay.
No, the effects are broken out into equivalence classes because I can represent them directly in the graph. So effects like reading and writing, writing standard out, and the effects of
Okay, so it's like a
writing,
union find.
no union find. This is equivalence class breakout. Because they're equivalence classes, if you're in one class, you're guaranteed not in any other. There's no may or might. There's only yes or no. There's only must or must not.
And then your node has like a pointer to some other node that represents its equivalence class. Is that what your effect edge is basically?
Yeah, it's a memory edge is a pointer from the node that defined the prior value in that equivalence class to the current node. So load has a memory pointer. He points to typically a store that defined a value for that equivalence class that we're talking about. Um, maybe it's a fee function that merges two different stores. Maybe it's a call entry header that said this is the memory that came from the
Hmm.
call header, but it's the prior definition for that equivalence class slice. And
There's
then
probably
however
something.
finely grained you can make those slices is how precise your aliasing is.
Yeah.
There's
This
probably
is
something a little
interesting, I think.
subtle going on there. To clarify, earlier you asked about like, well, you would need to if you wanted to track like sort of indirect relationships. Well, here's the deal. So you've got your entire edge graph here. You just take the subset of your graph that represents memory, and then boom, that's your edge graph as a whole. Now, when it comes to things querying it, things like peepholes don't necessarily need to query the entire graph. They ideally don't. They can query some parts of it, and because the graph can tell you what events lead to certain things, you can then do all your local things. But now here's the deal. Whenever you update the graph is always true. And this is the important part for the no side structures thing. The graph is the ground source, which means that if somebody wanted to do scheduling, if somebody wanted to run global code motion at any point in time, they could get themselves oh, here's what the graph is supposed to look like scheduled. Because they can say, hey, here's where all the loads and the stores, here's where the dependencies are. This load is dependent on this store and things like that.
And I have that in simple. I can hover my mouse in the debugger and get that dump every time, always.
It is a little bit I feel like that specifically is maybe not something that is entirely dissimilar from having a side table, other than maybe it's slightly cleaner to work with, which I mean it's not something that should be discounted.
I've done the side table thing in the past, and this is way the hell cleaner to work with.
Yeah, it avoids the caching issue that, for instance, so LLVM also has a memory SSA, but not all passes agree to use it, which means that sometimes it gets invalidated. And so when you have side tables or side structures that you don't always guarantee to be truthful, then you have to either deal with synchronization errors where, hey, this table is no longer valid, let's reconstruct it from scratch, which might throw away information, or you might run into cases where they disagree with each other, and now they're just potentially lying to you, or you run into phase ordering things where somebody decides to take one of them to be truthful, the other one also says truthful information, but less information, and in which case you lose information, even though neither of them are lying, they're just one of them is just less right.
But like theoretical bug, right? Say I do my pass that does all of my memory aliasing analysis, right? And I build these equivalence classes. Then I run some other pass that adds a bunch of nodes, right?
No, you don't do any memory aliasing analysis. Never. That's the joy of type-based aliasing. You get it.
Well, but you need to build the equivalence classes somewhere. I mean, okay, so if you're assuming type-based aliasing,
no. You get it from strong typing, which
let's say we're not assuming type-based alias because not all languages have that, right?
I get it, but if you're a strong typed language, then type-based aliasing is literally free out of the parser. You do nothing; the parser throws it in your face. You can't dodge it.
So I'm
don't
really
just using
aliasing
so I can try to engage
right?
with the I can walk through the other side of things.
Like generally, let's say we have some pass that establishes some connections in the graph,
the parser. He does all the aliasing for free as all the other graph edges. He builds all the graph edges.
But separate from aliasing, let's say there's just any other product that we want, anything that makes things easier. I don't know, I have a bajillion products in my IR. I compute some special hash to make the strength reduction faster and stuff like that. Anything where there's some invariant that you establish. I don't know,
Don't. That's the trick.
Just no invariants.
Side tables, and I don't.
Well, actually, I'm really curious about this example. Let's walk through one with the strength reduction thing.
Well, I mean, basically, it's just I think that one is pretty easily solved with phase ordering. But for example, so the way that my strength reduction works is I just have this big table of rules, and then I basically compute this kind of fuzzy matching magic number so that I can, as well as a hash, so I can very easily index into my table of rules by opcode or whatever. And this, I do some people optimization until fixed point basically. So for something like this, I mean, I think it would not be the hardest thing
to a fixed point, and it covers my strength reduction.
So I think, let's assuming that I do not change that aspect of the implementation, it seems like it would be logical to basically add a field or something to the node, which is essentially the same memory overhead as a side table. So I think that's not a clear win or loss against sea of nodes.
Okay, so here is a place where I use side tables. For instance, the register allocator as a separate standalone pass definitely makes side tables of things that I want to know about what the hell's going on. I don't modify the graph during register allocation except for very narrow specific targeted I inserted spills. And then at the end of register allocation, I throw the table away. And it was register allocation as a one and done thing in a compiler. So
there's a closer equivalent, which is when you're doing global value numbering, you keep a hash table of the nodes and stuff like that. The peepholes themselves modify a node. So you pass them in a node n. then they will pass you back a node k, which may be the same node or a new node. Because it can be the same node, that means generally speaking, you'll like just you'll preemptively throw out the thing or invalidate the data from the from the table, and then you'll re-add it.
Yeah.
Um,
I'm looking at the global value numbering code in simple on the screen now.
So that's a side table, but because throughout the entirety of peephole time, we can just say, hey, we know when nodes are going to be modified because they're only modified by peephole rules. In this case, it's a pretty cheap side structure to maintain. So we do have side structures at times. But the important thing is to especially keep down the amount of mental overhead you have to like uphold when you're dealing with them.
So it seems like this is what I'm basically getting from this is that what this basically imposes is that you just have to write your passes in a certain way such that you essentially never, like, for example, if I computed GVN, but I had several variants of peephole, like if I had like a peephole optimization pass, but then also maybe like a separate like dead store elimination pass, and maybe I query my GVN in both cases for some reason, right? Like in the wealth of possible implementations, we might reference this multiple times.
What the passes do change between the sea of nodes and not, because many things that other people call a separate pass just become yet another peephole, and the one peephole pass runs everywhere, always, anytime you want, for sort of basically for free. It's always the sum total.
I think there's some pros and cons to this. There's an obvious pro, which is, you are avoiding basically this, a lot of cases of phase ordering, if not all of them, depending on what passes you run, where you basically say like I've fused everything that will use this data of like GVN or something into one pass.
Essentially prove that I have fused all interesting passes except for a whole lot on CodeGen at the back end where I register all Kate in code, and things that inflate code, which would be inlining and loop unrolling. All other things, literally all other things, fall into the peepholes, and I can prove that they are all deterministic and completely phase order free.
Yeah, I break down my categories into like so I've got like the pessimistic passes, which are basically just peepholes. Then I've got like my optimistic constant propagation, stuff like that. So those have to be separate. And then I have my loop passes, inlining, and then I guess the machine CodeGen is technically its own thing. It's its own flavor of stuff. Yeah. But so I get like 4-ish groups there. Peepholes makes up the overwhelming majority of like all of the work. The loop stuff does a bit of analysis, builds up some stuff, maybe vectorizes a few things, cleans up some like loop headers and rotates and stuff. Optimistic does a few constant propagation finds. Usually it just tells me that things are like not nan, which is actually kind of useful. But yeah.
But David, you had something you're about to say.
I think the case that I'm still thinking is kind of a difficulty with this, or I guess this is what I would say is maybe a constraint. And so like there's a lot of benefits to sea of nodes, but like one constraint is in compilers I've worked with in the past, we have a fair amount of passes that we run like mutually to fixed point. Right. And so for example, like we might find like maybe some peephole optimization eliminates some problematic instruction, and then because that instruction is actually eliminated, it allows us to do like another escape analysis that we were not able to, that we didn't know we could do previously. And then maybe once we do that, it creates another peephole optimization or something like that. And it seems like if you want to do that in sea of nodes, you basically have to make sure that these are fused into one conjoined pass, right?
To be fair, that's technically how you solve like all of these fixed point problems, which is that you combine the passes. Yep. There's 2 different ways of combining passes, and there is a there's a good way, and there's the way that you do when like you can't do any other way. So the way that you do when you can't do any other way is that you just run them back to back, both of them, until they just stop doing anything. Yeah. But if you can do better, usually you do like a function composition of both. So every time you do, like let's say with peepholes, I have a pass that does multiplication. I have a pass that does addition operations. Okay, cool. If it's an add, do the add. If it's a multiply, do the multiply, and do those both in the same pass until like they solve. I guess another example is, hey, I can do constant propagation, pessimistic kinds with the pessimistic, reassociations and all of those other algebraic whatevers. Boom, throw that in there. And so I keep throwing things into the soup that's like peepholes. And in which case, that's the way you would resolve that. There's things that fit outside of that camp. But the thing is, Phase ordering becomes drastically simpler when we break it down into there are 5-ish passes of like pessimistic, optimistic, inlining, loops, and machine CodeGen. Once you have like 5-ish passes as opposed to the like let's say the LLVM equivalent of like 70 to 200, you're just in a like different like ball game in terms of figuring these problems out.
And
Somewhat.
all
I
the
mean,
examples,
I think I would dispute that those are equivalent. Like, you
all the
know,
things that you pulled up so far are all things that fold easily into the peephole realm and are in simple in the peephole realm.
I
And
think there's a
so,
difference though between you can do something versus you get like the truly most optimal code. Like I think,
okay,
like you can
here
get really good performance, and I definitely am not going to dispute like you can get
here I'm
pretty
gonna
good high
I'm gonna
quality.
push on you a little bit more. I have in simple the thing that says all peepholes will run till none apply, and it doesn't matter what order you run them, you get a canonical answer out with all peepholes maximally applied. That is where I'm at right now. That only breaks when you have code inflation, which is really inlining and loop unrolling, which do have issues with what order they come in and how fast they go. All other things, including all your little escape analysis things, where I have a little piece of code that I can now prove goes away, so I can now do more aliasing, those all just fold into the peeps. Hard guarantee, theoretical guarantee that you get the maximal best answer, irregardless of what order and what peeps are involved.
Yeah. I could also give
I
another example.
mean,
If you've got ints combine in LLVM and you've got the what's it called? Different flavors of they have a few different flavors of global value numbering and CSE passes. A lot of that work just gets moved over to ints combine, which solves for better answers far more quickly.
I think the case that this is more efficient than something like I don't know. Like, or I definitely see the value case here. I think the thing that I'm a little bit like cautious of is mostly my current tack when approaching my compiler backend has been, well, essentially, if we are just like really strategic about phase ordering, maybe there are some cases where we have a lot of passes that strictly just don't need some information to be kept around or something like that. Or maybe there are some cases where it actually is useful for us to repeat some work and do some more sophisticated work, even if it is actually invalidated somewhere else. Like my effect analysis is pretty fast. I might need to regenerate it at some point, but even if I regenerate it, I'm not entirely convinced that like it will actually be slower to do this really specialized, just talking to this one array, really small, like hot loop of doing my effect
The
analysis versus
difference,
having to do this big branching thing that's fused with my people opt.
the thing I think is different here is that you looked and I didn't. I got the aliasing perfectly done from the start. I never had to look at any side structure.
Well,
How
I
cheap
think
it was,
perfect is a bit of a tricky thing.
didn't
Like I think,
didn't make
there are this is maybe one of those other cases where it comes down to your source language a lot is if you do type-based aliasing, then I think that gets you pretty good aliasing classes in a lot of cases. But
I,
anywhere where you have the same type of thing, it doesn't
the
really do so
the
good.
IBM tried really hard on getting better aliasing in the 80s and 90s in their compilers. And all throughout the journey of Hotspot, there was competition with IBM Labs to try to do something better. And IBM proclaimed pretty aggressively after a whole lot of hard work that type-based aliasing got you roughly 95% of what you could get out of the best possible Oracle aliasing.
Well,
And
and that's for Java, right? Like,
no, Fortran, C, all their classic
interesting.
languages. If you could get type, you had to, C had to be perfect. You had to say strict. If you were the really strong type language, type-based aliasing got you the vast majority, vast majority, what you could ever get. You could get better, but not for very much, except around a big arrays. And then big arrays still need to do vector dependency analysis.
I would even
I,
yeah. I wouldn't even see the battle of like that the aliasing of that kind is even something that you can't do. So here's a fun case that I like ran into sort of accidentally. So in CF nodes we have these concepts of being able to have memory edges and stuff like that. There's also the notion of being able to split and merge a memory edge, and in which case you have two parallel timelines of memory effects going on
yep.
because they're not dependent on each other. If any of them do peepholes to check for like, hey, has anybody stored to this location? They don't have to check any of the paths that are not in their way.
Yes.
They also don't have to, scheduling wise, the same thing is true. So they're partially ordered against each other. And it's just because they just don't connect. But now here's the fun bit. Let's say in Rust and in C99 we had this concept called restrict, where you could say, hey, within this scope, certain pointers that are being written to do not interfere with pointers that are being read from. So like a restrict pointer is logically not aliasing with anything else being read from, which is huge, very useful. Compilers do not support this feature very well, if not at all. I think LLVM has given it a few jabs and it's like gone poorly. And this has become a problem for Rust because Rust really wants that feature because they use it for their aliasing. Hey, we have mutable objects. Since they're single ownership, it means that we know that nobody else is aliasing. Huge, huge benefit. And this is something that you can't necessarily get out of type-based aliasing, but you can get it out of splitting and merging. So now what you do, take a scope, split the start of the scope, and now take all of your non-aliasing stores and put them on separate parallel timelines from the what's it called, the loads, the non-restrict loads, and boom, you've got yourself aliasing that is now your scheduler is aware that like the two things do not interfere. Your peepholes are aware that the things don't interfere. Any of your load, any of your memory passes are aware of this. Any of your inlining, everyone is aware of this. And because things like scheduling don't depend on querying any sort of structure, they just depend on the graph dependencies. Yeah. They already have the answers. They already know, oh, I can schedule these things against each other in all sorts of weird ways. If you're on some weird processor, let's say you're on a DSP and you say, hey, well, now that I know that these things don't alias, I can actually issue both of these at the same, like on the same cycle, on some like VLIW. If you wanted to say, hey, do load elimination on them, they both don't interfere with each other. And you know that, even if they share the same type, because you've told it.
I mean, I could pull up my slides for splitting memory edges for type things.
Yeah. And so if you wanted to represent fancier concepts of what's it called, like memory aliasing, LLVM has tried with a few different strats to do with encoding scopes into their graph. But then those things start to break down when you start interfacing with other aliasing strategies, like for instance the memory SSA, because these things aren't both in agreement on what the truth values are. The splitting of memory is wholly in agreement, and everyone in the graph knows because everyone's playing by the same rules.
Yeah.
It is definitely a compelling idea. I appreciate the effort into selling me on it. I'm getting a little bit convinced.
Let's not beat on you anymore. I think that's not going to be productive for either of us. I have some talks that break it down the hows and whys of how memory aliasing goes. If you care, I can show them next week, and many people have seen them, so maybe you want to see them online instead.
Oh yeah, I can. I don't mean to make you just retread stuff. I feel like I worry I've been making you retread a bunch of stuff already, but I think I can definitely check out some talks. Or I don't know if you have a link that you could put in the Discord or something.
You reach the point. I'm able to find a link here. You reach the point where a lot of the things that are really interesting are accessible to you in a deeper way. A lot of people get the surface look, but they haven't dove in and written the compiler and played the game. And you're in here playing the game now, so there's some stuff that's now you're asking the questions that make sense to what the hell's going on with CO's nodes, and so more information might help you. I'll throw the chat link, but this is the standard slide set I've used. Well, I will, except that it won't let me. All right, I'll sort it out. I'll throw it in the Discord. It's been in the Discord.
Yeah, this can be done
too.
asynchronously, right?
Yeah. It'll come around. Yeah, this is fun stuff. And maybe next week I'll work through a debugger example where I walk through people optimizations doing strength reduction and load store, aliasing stuff, all that kind of things. It's pretty easy to set up and run.
Well, and this has definitely given me some stuff to think about. Like, it's been a while since I've really been working on my back end. I've been doing a lot of just front end safety analysis stuff mostly lately, but my back end has been kind of languishing for a couple months. So this is giving me some thought. I should, I kind of want to see just sort of what the logical conclusion of my current approach is, and then see how much it sucks. I mean, also I probably need better benchmarks, but
yeah, well, I mean, I have no code, so I have no benchmarks. So
I am definitely very open to the idea of what is the ideal aliasing strategy for a given language or something. And it could be I currently don't do type-based aliasing. I probably should be doing type-based aliasing. It probably would be pretty easy. I've been a little tentative because I think, my language supports some limited memory on safety, even if it's kind of not really meant to be on the hot path. But theoretically, in a lot of cases, it should be able to work. I don't know. Anyway, there's a lot of stuff to
Yeah,
investigate.
right. Yeah, no, right. Life goes on. You get all these things to go after. I played hard with the classical alias analysis things in the 80s, 90s, and 2000s, and my experience with Hotspot just hard flipped me over to type-based as not only good enough, but essentially free and bug-free because there's no side structures, there's no stale things come out of order. The graph is the ground truth. You modified the graph, you modified your aliasing, but you modified your program all
Yeah,
in
yeah.
one go, and da 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 da. So I got sold 20 years ago.
I think my question for myself is, why not both? How much of a benefit do you get by doing both? How expensive
No,
is it to do both?
I tried. There is. No, I took some of the what I called Oracle level aliasing into C2 in a couple key places to see if I could improve my life. And the answer was the vast quantity of bugs that came with it just wasn't worth it. The always correct aspect of the aliasing as it stands in the graph is a huge win, and it lets you get your head in another space. You get to a place where you can do better optimizations all over the place because you're not fighting the aliasing. It frees you from the aliasing being tricky, buggy, hard to manipulate, hard to reason about. It becomes trivial and then becomes a non-problem. And then you realize you can do all other things. And the aliasing doesn't have a lot of gain to be had by having a better aliasing, except in the one path of vectorized math ops, for which you do a specialized
Mhm.
vectorized math op pass, which is
There's actually that actually reminds me of one last thing because I love memory in Sea of Nodes, but it's basically so if you preserve since you've got your memory graph and you built your nodes, your machine nodes out of your ideal nodes, they share the same like memory graph effectively,
yeah, they do.
which means that if you were to choose to do, and so this is something I actually do, which is that I do instruction selection on the unscheduled graph, and then I do code motion for
I'm
like flattening
I'm
it
doing
on the machine graph.
I'm doing
Um,
same thing in simple.
Fun.
yeah, and so what that leaves you with is your code structure in terms of things like if you want to hoist things in and out of loops, or if you want to do local scheduling, and you want to if you want to like fiddle with certain things. So for instance, I've got certain operations that might expand out into a few different instructions. An example might be if I do a local like a thread local load that takes like I think like 3 or 4 instructions, but like some of those can be shared actually across multiple different thread locals, so they can actually be hoisted by the machine nodes because they know that like, oh, those are identical instructions. Even if they like, they don't have to know that much about the instructions. They just know that, hey, these are 2 identical instructions. Let me just hoist them. And
Yeah,
so you get a lot of fun things like that. And then when it
This is all
comes to like,
pre-register allocation, right?
yeah,
yes,
yeah.
although you could even do
Okay.
scheduling post-register allocation, you have the same graph, and all you have to do is just make sure you don't break any of the register
Break out
anti-dependencies.
things. Yeah.
Yeah, yeah.
Yeah.
I could see how maybe you could get it working either way. I've
Yeah.
honestly been a little unsure if I should even bother with scheduling at this point, because I've heard it's kind of diminishing returns on modern hardware. But some of the stuff like hoisting thread local
You
cache
must do
access might
something
help.
coming out of Sea of
Yeah.
Nodes. Sea of Nodes throws all scheduling info
Oh,
away.
from Sea of Nodes, yeah, you'd have to.
Have to.
Yeah, but like the heuristics you use might be like particularly weak. Just like, oh, hoist a few things, keep some things
Yeah.
in loops or whatever.
I do a
Not.
dumbass loop. I'm sorry, list scheduler for local scheduling, and it's just a
Mhm.
dumbass list scheduler, and that's
Yeah, yeah,
Yeah.
yeah. Like, I think the spirit of scheduling in the sense of I want to like order things so that things are dispatched in a certain way to try to get more performance is the questionable part, not the idea of just, oh, I need to pick a
Yeah,
schedule
yeah.
for my graph. Which I
There's
also have to
a
do,
few
right?
spaces. So one of the weird, annoying things in the world is that we've got a lot of processors that are still in order, and some of them are like dual issue. So like half the cores on my phone are in order, like dual issue. So scheduling there is basically just, hey, make sure that if there's 2 independent instructions, put them next to each other, or else like it will stall on the first one and then not see the second one, even though I could have done both at the same time. I saw like some random talk about RISC-V where they were doing that for LLVM because they kept running into this with like random hardware because, unfortunately, the space of RISC-V is riddled with a bunch of these in-order processors,
Oh, yeah.
and so is the space of cheap ARM processors.
Yeah.
So it does matter somewhere, just not on like
the
desktop.
embedded things on the planet all start single issue, then they go dual, but in order, and yeah.
Yeah. I think the like classic result that I think, there's like a classic paper that's like, what is the right balance of like scheduling versus register allocation? Because if you're trying to maximally schedule out your operations so you can do the most work in parallel at once, that also means you're applying the most register pressure. And so there's kind of conflicting
Yeah.
things where like,
Well,
probably having the extra register pressure is worse for any out of order processor, or at least like a really modern one. And
Yeah.
somebody with a
There's
lot of
if you're
there's like a fun
optimizing
way
for
to
that, then
like you can tweak heuristics on like a list scheduler to basically say like, because like let's imagine you unroll the loop way too many times and now you've got like a super parallel super wide thing. It's
Yeah.
like, okay, well, mathematically it was originally a thing that fit without doing spills, so there is a way to schedule it where you could get that, and so you kind of just
yeah.
have to like figure out how to min max like
Yeah.
schedule it such that it like goes as wide as possible with the registers it has before it like reaches over the pressure where it needs to spill again, because you really don't want to spill.
Yeah.
Yeah.
It's a
All right.
nightmare, but like if you really get finicky in that space, then there's some research in that.
I have things to do. You do too.
Oh yeah, sorry, we're over.
This is like fun stuff. And of course, there's Discord if you want to go on Discord and go to town there, including switching from Discord to Discord chat or Zoom or whatever. So it doesn't have to be the end of the conversation, but it's the end for me. Um, so that's it. It's been very fun. I've had a great time, and I hope to see people next week.
Yeah, thanks for the great discussion.
Yeah.
Bye.